In this lesson, we're going to look at universal gravitation. Now, we are familiar with the idea that gravity is the force that holds us in orbit around the sun and the moon in orbit around the earth, but that wasn't always the case. Newton was actually the one who developed the idea that the same force that can pull an apple out of a tree and cause it to fall to the ground can act over a long distance between Earth and Moon and actually hold the Moon in orbit around the Earth and the Earth in orbit around the Sun. So Newton, when they say he discovered gravity, that's not what they mean. What Newton did was he said gravity is universal. Gravity acts between all objects with mass. Okay? So it's an attractive force and it acts between all objects with mass. And Newton did the math and took it a step further than that. And what Newton figured out was the force due to gravity, which I'm going to go with a capital G here. This is gravity in general, not just Earth's gravity. Is actually, Newton didn't find an equality. He found a proportion. So the force due to gravity is proportional to the mass of the two objects divided by the distance between them squared. Now, he did this through studying the motion of the moons and the planets and figuring out how these relationships worked, but he did not have an equality. He had this proportion. He knew that the force of gravity was proportional to the mass and the distance between them squared, but he did not actually have an equality. And it took 100 or so years before another guy, Henry Cavendish, actually figured out a way to measure the constant that would actually let this be an equality. And he came up with the force due to gravity is equal to the constant g, and that's an uppercase G, not lowercase g. It's not the acceleration due to gravity. This is a universal gravitational constant, times m1 times m2 divided by r squared. Now, what Henry Cavendish did to measure this universal gravitational constant was pretty cool. He suspended off of a cable and a crossbar a couple of heavy masses, and he put a mirror on this cable so he could shine a light at it and it would reflect off. And he did that so over here he could measure very small angles that this thing would turn through when he brought up a second mass over here, and so that he could measure how much torsion it took to turn that cable, and he could therefore measure the force of attraction between these two masses. And from that, he was able to calculate this constant G. And we know it has to be very, very small. And the reason we know it has to be small is we do not feel it in our day-to-day interactions. You don't feel a gravitational attraction between you and your pencil, or between you and the person next to you. You do feel a gravitational attraction between you and the Earth, because the Earth has a whole bunch of mass. So compared to everyday masses, this has to be a very small number. And indeed it is. G, the universal gravitational constant, that was an awful G, is equal to 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Okay, and the units on that do matter. If we switch systems, we'd get a different constant. And so what this allows us to do is actually measure or calculate, I guess, the force of attraction between all objects with mass. And this r, this distance between them, that's the distance between their centers. So when we do these problems with Earth, we have to take into account that an object on the surface of Earth is not an Earth center, and there will be a non-zero r even though we're on the surface of Earth. It's not measured from the surface, it's measured from the center. And so if we actually take a look at what I mean, so here's Earth, there's its center, we've got this radius r, and here's a second object. So the mass of Earth, we're going to call that m1. We got our second object, m2. We know that the force acting on m2 is equal to ma, m2a. That's Newton's law, second law. Now, if that net force is only the force due to gravity because it's in free fall towards Earth, then we can also say that that net force is the force due to gravity, which is Fg. So we have Fg equals m2a, but that means Fg is mass of the Earth, mass of object 1, times the mass of object 2, divided by the distance between them squared. So even when these two things are touching each other, it's measured from the center, so that's a non-zero distance, equals m2a. And I have g in here, right? Okay, so g m1 m2 over r squared equals m2a. You'll notice that m2 is in both terms, so it drops out. And so we get that g times m1 divided by r squared equals a. Now, if you look at what that is, that tells me that the acceleration of any object on or near Earth's surface only depends on the mass of the Earth, that's m1, the universal gravitational constant g, and r squared. But if we're on or near Earth's surface, that r is constant. And that's what we know. We know all objects on or near Earth's surface fall with an acceleration of g, or 9.8 meters per second per second.